So the NOAA ozone instrument, it's an improved version of the standard 2-channel UV absorption measurement that goes back to sort of the first real quality flight instruments that were used to diagnose the ozone hole and ozone loss and things like that. So the Global Hawk is a good platform for measuring stratospheric ozone because of the altitudes at which it flies. It flies in the lower stratosphere across a wide range of latitudes, and so with an in situ measurement we can make high quality ozone measurements that can be used for comparison with satellites or with sondes and things like that. Because there's this strong gradient in ozone from the upper troposphere into the lower stratosphere, that by measuring the ozone we can try to determine the source regions of the air that we're flying through. So if we see lots of ozone in the air that we're sampling, we know that we're not looking at tropospheric air that's moving up, we're looking at stratospheric air that's sort of come down. If we see relatively low levels of ozone, then we know that we're looking at tropospheric air that's potentially on its way up and in the process of being dehydrated before it reaches the stratosphere. The NOAA UAS ozone instrument flies in this zone of the aircraft for the HRX mission. It's what we call an in situ measurement. It's not a remote sensing instrument, so we actually pull air into the instrument, do an analysis on that, and then let that air back, send that air back into the atmosphere. The ozone instrument is a 2-channel UV absorption instrument. So the air is pulled in through this inlet. The aircraft is flying along this way. Ram pressure basically feeds into the inlet. It's choked back here so that there's a high pressure inside the inlet here. And a portion of that flow then passes through this tube into the instrument, goes through the analysis cells, then comes back out through here and is exhausted in this low pressure tube. So the air that goes through is split into 2 paths. One path goes through an ozone scrubber which catalytically destroys the ozone, and the other path just goes straight into the cell. So at any given point we have 2 parallel absorption cells, one of which has air with ozone and one of which has air that has had the ozone catalytically removed from it. And then we have a pair of valves that switches the flow between the 2 cells. So each cell has a 10-second period of air with ozone and then a 10-second period of air without ozone, and it goes back and forth. And then we can use that difference in absorption from the air that has ambient levels of ozone in it to the air that's had the ozone removed to make a measurement of the amount of ozone that is in the air. The way the measurement works is that ambient air is passed through a cell, and the absorption of light is used to determine the amount of ozone in the cell. Because of the constraints of working on the aircraft, we're limited to the length that we can make our absorption cell. And normally we'd like it to be longer in order to make a better measurement. But in order to work with that sort of fixed length that we have based on the depth of the bay that the instrument sits in, what we've done is we've arranged it so that the light enters the cell and passes down the cell and then is reflected at the other end to double the useful length, the absorption path length within the cell. The NOAA UAS ozone instrument that's flying the Global Hawk for the HRX campaign is a high accuracy, high precision, relatively high frequency measurement. It makes a 2 Hertz, makes measurement twice a second. So we have a good record of relatively high resolution measurement of the ozone in the air that we're flying through. And it works well in conjunction with the water vapor and water measurements that we're making because the troposphere is wet, the stratosphere is dry. The stratosphere has a lot of ozone, the troposphere has a little bit of ozone. And so using those 2 variables together, we can start looking at sort of the mixing and say, what's the stratospheric influence in the air that we're sampling versus what's the tropospheric influence in the air that we're sampling as we're in this region that's sort of in between the troposphere and the stratosphere, in the tropopause region.
Yeah, so water plays an important role in radiative transfer in the stratosphere. And so basically one of the things we're really interested in understanding with our measurements of what are the physical processes that control how much water vapor can get from the troposphere up into the stratosphere. So our instrument actually measures two things. One measurement we make is water vapor, and the other thing we make is what we call total water, which is the sum of water vapor plus any condensed water. So if there are ice particles that the plane flies through, the instrument will ingest the ice particles, the particles evaporate, and then we measure that as well. So it'll tell us, A, are we in a cloud, and then give us information about how much water is in the condensed phase to compare with the water vapor. The way it works is this part of the instrument is inside the aircraft. The skin of the aircraft is right here, and then this is outside. And we have these two different inlets. So this is the forward direction for the aircraft. And to measure water vapor, we sample from this port. And that means that if there's any particles or anything, they go right by it and they don't get sampled inside. So that's just vapor. And then to get what we call total water, that's this forward-facing inlet. So the particles and everything will go straight in, evaporate, and then be sampled into the detection cell. And so we have two pumps that sample gas in. Gas comes into the instrument, and it goes inside this box here where we have two different cells where we use a tunable diode laser to quantify the water in the cell. It's infrared, it's absorption in infrared, so we have a laser that's around 2.7 micron, and this is basically a location in the infrared where water absorbs very strongly. So we scan the laser across some wavelength, and we see this big absorption at a specific location. So yeah, the laser wavelength is being scanned across a couple of wave numbers. And you see this sloping baseline, and that's just because the laser power is changing. But right in this small region right here, you can see there's a big bump, and that's where a lot of light is being absorbed. That's because water absorbs really strongly in that location, and also in this location as well. And so we measure water at these two different places. We measure in two different places because the concentration of water vapor that we go through in the atmosphere covers a big dynamic range. So we're really sensitive right here, and then when we're close to the ground, we want to be a little bit less sensitive, so we use this line here. It'll certainly help in planning the flight. I mean, the fact that we have this total water measurement, so we can tell, are we in a cloud or not, should help the flight planners quite a bit. Because they want to be able to fly into these clouds that are what they call subvisible, so you can't see them with the satellite. A lot of times you can't see them with the camera, but we can tell them, are you in the cloud or not, and so if they are, they can choose to stay in the cloud or leave the cloud. So that's going to be a big help, I think.
Copy. Configuration is complete now.
So we're ready for aircraft taxi prep.
Copy at work.
NASA 872.